This is the fifth in a year-long series, a year-long six-part series on climate change and security that's co-sponsored by the Dickey Center for International Understanding. And within Dickey, then it's the War and Peace Studies program and the Institute for Arctic Studies that are collaborating on this. This is an attempt to put together groups of people and ideas on campus to do something new and interesting and a little different. Thus far, the series has covered a broad range of topics that range from the scientific evidence that human activity is contributing to climate change to the consequences and impacts of climate change. In the Arctic area, which of course is central in the Arctic Studies program, on sea lanes, on global disease patterns. Today we're going to hear from Professor Henry Jacoby from MIT about alternative policy measures for mitigating climate change. And mitigation in climate change mostly means reducing greenhouse gas emissions. Dr. Jacoby did his undergraduate work in mechanical engineering from the University of Texas at Austin. He holds a PhD in economics from that Crimson place down south. He's been working for decades on questions related to energy, natural resources, and the environment. Now, I should say that I myself am an economist who specializes on the economics of energy and the environment. People who come to this issue afresh see this as a new issue. But researchers like Dr. Jacoby have been working on this for 30 years. Is that fair to say? Certainly looking at energy and the economy is something that economists have been looking at since the oil shock in 1973, and the environment has always been a big part of that puzzle. And Dr. Jacoby is a veteran from the trenches and, in my opinion, a true leader in this field. Professor Jacoby is, he's the professor of management at the Sloan School of Management at MIT, and he co-directs the program on science and policy of global climate change. And without further ado, I think that I'll simply turn over the floor. I'll say, though, that his current research is focused on the economic analysis of climate change and greenhouse gas emissions control, and that's his topic for today. So welcome.
Okay. Well, thank you. I'm very pleased to be invited to talk to the Dickey Center, which does such really great work in these areas, and I'm also pleased to have a chance to visit Dartmouth on a day like today. Choosing the right day is crucial. Before I start, I say a word about what the joint program is, because it is the source of what I have to say. That's this joint program on the science and policy of global change. It's a group at MIT that's actually been in existence for 17 years, integrating the climate sciences, because we have a department of that at MIT, and economics and management and the social sciences and policy analysis, putting those things together into an integrated analysis of the climate issue. So I should start with truth in advertising. I'm going to say some things about the science, but I'm an economist. So you're hearing about the science from an economist, and if there are scientists in the argument, in the group, in the audience, I'll be happy to take any assistance you can give me. So, what do people think about the climate issue? There's a kind of a litany that you get in this area about whether or not we should take it seriously. People say, well, it's not proven, or if it's proven, well, it's not that serious. If you've watched newspapers and the news, you hear these arguments. Well, but if it's serious, well, it's too expensive to fix it. Well, maybe it's not too expensive to fix it in the United States, but if we did, the Chinese won't. And it's too late anyway. Right? So we'll talk about this. So let me start. You've already heard from, I realize never doesn't come to the same thing, but you've heard from Steve Schneider. If maybe some of you heard from Steve Schneider, I won't repeat what he has to say, but I'll give you our view of the level of risk in this area, which is, and I would say that if you carry anything out of the door from here, it is that this issue is to be viewed as an issue of management of risk, management of global risk. And we do a lot of work in this area we're using models that we developed to try to understand what is the level of risk in this area. So we do a lot of uncertainty analysis in this. And our way of expressing what the risk is we face is we do a common thought experiment in this area, which is to say, what would happen in terms of global temperature if we did nothing for a century? Now, we're not going to do that, but that's a kind of a thought experiment about what the risk is, and this is our way of stating that. We're running a global risk, what you can think of in terms of a roulette wheel. By this analysis, which I will say we've superseded this analysis. I'll say more about that in a moment.
Schneider showed us this incidentally.
Did he use this picture?
Oh, I think so.
Okay, well,
He's giving you credit.
We're getting out there. So there's some chance maybe it wouldn't be too bad. Maybe 1 degree, 1.5 degrees C over a century. That's not far from what we've seen in the last century, so that wouldn't be too bad. There's some chance maybe more than 5 degrees C global. Deadly serious business, and a large probability of changes above 3 degrees C. One of the points that I'll make here, since this is a group of organizations that has a big concern with the Arctic, is this is the global mean. If you want to draw this picture for the Arctic, you have to multiply all these numbers by 2. That is, the change in the Arctic is roughly twice the global average by most analyses. And that's why we're seeing the early signs of change in the Arctic. There are a couple of reasons for that. One is that the tropics have an air conditioner. The tropics have a way of sending the heat to the poles. Right? They do that with ocean circulations, and they do it with air movements, with storms, which is what we see passing by in our weather. Also, the Arctic has an air conditioner that we would be losing. That is the sea ice. The sea ice is a cooler for the Arctic. So as you have warming, you lose the sea ice, so you lose all that reflection in the summer when the sun is up 24 hours a day. So you get a lot more change in the Arctic than in. So those of you who are studying the Arctic, or this part of this program is concerned with the Arctic, the big risk early on is in the Arctic. Now, I will tell you that this is not our latest work. We have results which we are about to publish, which is worse. That is, the risk is greater than this. But for what I want to talk about today, this will be fine. Just imagine that this is not our latest work is somewhat more scary than this. The other point that I will make is this is not some risk which is going to appear, in some great distant future. This is a wheel we're spinning now. We are in this process now of changing the Earth's climate, going down this path. I have to turn this off pretty quick because people get sick in the audience. Now, to talk about this, I want to go to a scenario of climate impact of humans, and to show you what is involved in trying to correct this problem, manage this risk. And one way to start is the EPPA is just the model we use to forecast. And this is one scenario of CO2 concentrations if we didn't have a policy to control them. The world is now around, the total concentration in the atmosphere now is about 385. It's going up about 3 a year. And by this projection, we may be up somewhere around above 800 by the end of the century. It's a fairly typical scenario. It's okay for what we want to do. Pre-industrial, we were at 275. So we're already up substantially above the pre-industrial level. The Earth's CO2 concentration was around that level for the last 600,000 years. So we are substantially outside the experience of the Earth with CO2. Now, we have a climate treaty, and the climate treaty has as its main objective to stabilize this process, to stabilize emissions in the atmosphere at a level that will prevent danger to ecosystems, danger to economies. We determine what that level is, what we think is dangerous, but there's a frequently proposed target is we would try to hold this process at 450 parts per million, not let the concentration in the atmosphere get above 450. I'm not going to talk a lot about that We can talk about it in the climate, in the discussion period if you want. My own view is we're going to blow through that. We're going to blow through that target while we're trying to get a handle on ourselves. But we can talk about that. That's not a popular thing to say. This is the European target claims that 450 is the target, and because they associate that kind of average outcome with 2 degrees C above pre-industrial, but we aren't headed to do that. So let's talk about maybe a perhaps more realistic one. I'll use an illustrative target. We would try to limit the atmospheric concentration at 350 parts per million. 550 parts per million. And let's talk about what's involved in doing that. And what would we gain by doing that? Well, here's the previous roulette wheel if we didn't do anything. So in the sense of risk management, what would happen is if we could stabilize at 550, we don't solve this problem. We don't get rid of it. We manage it. We manage the risk. So given what we understand now about the responsiveness of the system, if we could stabilize concentrations in the atmosphere at 550, let's say between now and the end of the century or sometime in the next century, we would get rid of some of the nastiest outcomes. So the chances that it'd be a much greater chance that the change wouldn't be too great, and these really, really nasty outcomes like 4 and 5 degrees C, which used to be, that's about a 1 in 40 chance of above 5 degrees C, that we essentially avoid these nastier outcomes by limiting the concentration in the atmosphere. I'm going to come back and say more about that. One other thought about the Arctic. My colleagues who are the science folks say in this domain, in the domain of 4 to 5 degrees C, that's 10 degrees, that's 10 degrees C in the Arctic and in the Antarctic. We would, over some number of years, not yet known, we would lose the Greenland ice sheet. And we would lose a lot of the Antarctic ice sheet. So we're talking about many meters of sea level rise if that were to happen. Not according to the Gore movie necessarily, in 20 or 40 years, in some longer period, a few hundred years, but certainly on human timescales, we would see dramatic changes. So the Arctic is a big story here. Now, the questions. What if we took this seriously? What would be involved if we really took this seriously? What would be involved in actually trying to do something like achieving 450, taking some of these paths? And so, could we afford a major effort is a question related to my earliest slide. What about the winners and losers? Who are the winners and losers, and how would we deal with that? There's a question about, do we understand the scale of the task? So I'm going to talk about what the scale of the task is, and I'll use 2 examples. There are many things to talk about, but I'll concentrate on just 2. The notion that we would get the coal out of the power system by capturing the CO2 and storing it in geological reservoirs, and that we would get the carbon out of the cars, besides more efficient cars, with biofuels, which is the major way we're going. So we'll talk about those 2. Do we understand the scale of what needs to be done? And then there's a question of, I want to say some words about getting to an economic response. So I'm going to talk a little bit about public understanding and about policy targets and policy formation, largely to kind of just stir your imagination for some discussion of these matters. And as an example for a discussion, particularly of these latter parts, I'm going to use the current U.S. congressional bills, because there's a lot going on in the Congress. Not much going on in the White House, but a lot going on in the Congress. And what's happening in the Congress is that there's a lot been happening in U.S. policy. I don't want to say there's nothing. We've spent a lot of money on climate science, billions. We spend a good deal on technology, maybe not necessarily the most efficient way, but we do spend a lot of money on that. And we're doing a lot on subsidy of renewables, solar, wind, hybrid cars and the like. It's not that we're doing nothing, but we have not done the main thing that needs to be done, is to put a price on CO2. I mean, if CO2 is a bad thing to put in the air, then as an economist, I would say the right price is not 0. That's the second point to carry away. The right price is not 0. So The way we propose to do that is by the cap and trade system. Now, as I look around, I see a few people in the audience who probably didn't spend the last few months studying cap and trade systems. So let me just say a quick word about what a cap and trade system is. It's the way we regulate sulfur from United States power plants, and it's the big system in Europe. And it's the way you put a price on CO2. And the way you do that in a cap and trade system is you define some boundary within the economy. Here's one boundary that would include transport, industry, commerce, electric power, and government. It wouldn't be everything. It wouldn't include the households and agriculture. Or you could define another boundary, which is essentially the whole economy. And for all the entities in that economy, the firms and government agencies and everybody, you would set a cap. You would set a total that they could emit. And then, by some process, you put out permits for them to be able to emit that amount. And then, in order to see to it that the reductions are taken at the places where it's cheapest, you allow them to trade those permits back and forth. And the trading those permits sets a price. That puts a price on CO2. That gives the incentives for technology changes in behavior and the like. That's a cap and trade system. Vermont is a member of RGGI, right? Regional Greenhouse Gas Initiative. So and New Hampshire is a member of RGGI, and Massachusetts is a member of RGGI, Maine's a member of RGGI. So New Hampshire is a participant in a thing called the Regional Greenhouse Gas Initiative. That's because the United States government hasn't set up one of these systems. The states of the Northeast, it's sort of Maine and everybody down, and I think Pennsylvania is still not in, as I recall. Maryland is in. New York is in, Delaware is in, Connecticut, Rhode Island. And so these states have formed a system where they would form their own system, but only applied just to emissions from power plants. So you're in one of these systems, and they're going to begin to allocate the permits for this, I think, in June. So you actually have a system like this that the states are trying to create. The Europeans have a system called the European Trading System. It's the largest of these now, and it's part of the way that the Europeans are trying to meet their Kyoto commitment, is they have a system which covers large industry and the electric power. It's about 40 or 50% of European emissions are under this system, and it's operating. They have a price. There's a price of carbon in Europe. It's today $23 a ton of CO2. People are adapting to that. Now, in the U.S., there are lots of legislation. There are hundreds of bills and lots going on. But the major piece of legislation that's likely to become the basis of U.S. policy is a system of cap and trade. And there are lots of bills in there. There's going back a few years, there are various senators and representatives have had bills that didn't do the whole economy. They were closer to the European system in that the European system doesn't include transport. These include gasoline, but like that. There are several of those. There are other bills by Warner and Lieberman and Bingaman, which are upstream in the sense that they cover the whole economy. So everything is under the cap. So you can think of a cap and trade system as like a rationing system. You set a total amount, but you let people trade among themselves, and it sets up a market. And another feature of these systems, which is important, is that they allow you to bring credits in for what's called offsets or credits in from outside. So you might be able to bring in, you might be able to bring in permits you bought from this system, or you might, plant trees in Costa Rica and get credit and bring that in, or do some other outside activity and get credits that you're allowed to bring in to help meet your obligation. Right now, the key bills in the Congress, one is Lieberman-Warner or Warner-Lieberman, which is S2191. That is probably the lead bill, and that bill is going to probably get, there's some chance it may actually get to the Senate floor in June. It's not clear that Reid is going to bring that to the floor, but there's some chance he'll bring it to the floor. They'll bring it to the floor if they can get 60 votes. But they really need more. Of course, you need 60 votes to get anything through the Senate. But they want more than 60 votes. They really want a real push. So if they can get 80, 85 votes, they'll bring it to the floor. But the latest word is that it's not going to happen in the House. So so that, not in this term. So probably this bill, and it's also, there's some features of this other bill by another senator which are being integrated with them, and the politics is being played. Probably this is going to be on the agenda right at the start of the next administration in the spring of 2009. So this is the top item. So let's look at it. Here's how these things work. This is 1990. That's 2050. So they look out to 2050, and this is the total amount of emissions that would be allowed in the United States. And in 1990, this is CO2. We're around a little over 6,000 metric tons of CO2, billion metric tons of CO2. And over time, of course, our emissions are going up. So we're up by now, we're up around somewhere over 7. And these bills have different targets for what they would do. That is, the bill specifies that over time you achieve some reduction by 2050. That is the amount of permits that would be out there year by year would be gradually be squeezed down. And that then gradually gives higher and higher incentives to get rid of CO2, higher and higher prices of CO2, and the like. And different bills have had different targets and different paths. Some of them just stabilize emissions at levels today, and some go farther down. Most of them are around a 50% reduction by 2000, some as much as 80%. And this kind of language of reducing by a percentage by 2050 is very common. It's true in Europe. They talk about factor 4, which means reducing by a factor of 4 by 2100. Schwarzenegger talked about 75% reduction in California. This is all this kind of common use of these terms. And what I want to talk about is not that this is a bad idea, but what's involved in actually doing that. And I will point out that in the last G8 meeting, that is the last meeting of the summit last June, there was an agreement which our country agreed to, was we would consider seriously having global emissions by 2050. Now, the original text of this, Mr. Ambassador, said have global emissions by 2050. The seriously consider, I think, was introduced by the Bush administration. And you see again, I observe here the genius of diplomats, because they don't say half of what, half of something. But essentially, this is the global view. We want to go down by 50 to 75%. And depending on what you assume about how many credits or offsets can be brought from outside the system by, I don't know, fixing inefficient things in Eastern Europe or planting trees, doing forest protection and such. Depending on what you assume about that, the S2191, what am I doing here? The current bill with Warner Lieberman, which is the one that's really the first one out of the pack, is in this domain somewhere. So that's the major thing that's the major thing we're likely to do, and we're likely to do something like that. It's not impossible to get a bill passed in the summer, but the closer we get to the election, as you're all aware, the world gets crazier and crazier, and it gets harder and harder to do like this. So we have an analytical apparatus at MIT we use to study this kind of question. I won't spend too long on this, but I would say that to analyze these questions, our group has developed a bit of analytical machinery which has an analysis of the economics of emissions in the United States and in 15 other regions and such. Which that's the economic part. It's connected into analysis of the science, and I won't go into the details of this, but in order to understand this issue, just to give an idea of what's required, you have to understand about these CO2 and other chemicals in the atmosphere. You have to take account of what goes on in urban areas, because it has a big effect on the chemistry. There's dealing with the ocean. The ocean takes up CO2. The ocean takes up carbon, so the ocean circulations are very, very important. And then we have to deal with the land, and there's the issue of water and how the vegetation in the land changes. And we have to take account of things like solar, the changes in the sun, and changes in volcanoes and the like. And they're not so important to what I'm going to talk about now, but there are lots of feedbacks in this system. feedbacks like effects on agriculture and forestry, on hydrology and water supply, on energy demand, on sea level change, land use change, and the like. So we use this, we use this to look at what the effects are, the economics, the GDP growth, economic energy use, policy costs, and the like. The blue is a lot of climate things that we project, like global mean temperature, precipitation, sea level rise, ice cover, and then the effects on the terrestrial ecosystem, soil, vegetation, carbon, and such, which allows us to talk about agriculture and forestry. So this is, as you say, all singing, all dancing, modeling kind of thing that techie people do. But we use this, it's the basis of what I showed before when I showed my wheels. It comes out of a use of an apparatus like this. And so let me answer the question, or give our view of the question about could we afford to do this? What is the problem? What is the problem of trying to achieve these kinds of targets? And now I'm going to show you a piece of analysis, which is our analysis of that 50% reduction. What was involved in the United States to do that 50% reduction? And, well, what about the CO2 prices? Well, in these systems, you can follow the, firms and others could adjust to the targets year by year, or they could bank and save things for when things are tighter in the future. Since things are getting tighter in the future, firms would tend to bank. So that's the difference between banking and non-banking. But basically, you start with prices in the range of, let's say, $15 to $40 a ton CO2, and they get much higher as you get out to the end of the get up to the end of the century. So the European price is now about 23. It ranges between about 20 and 25. So it's really in this quite in this it's right in this range. If you $25 a ton CO2 is about 25 cents a gallon, but it's 1 to 2 cents on your electric bill. So it makes a difference in terms of the costs of things. So what would it do to consumption? By consumption, I mean the amount of money you have to spend. That is, how much would it lower the amount of income and consumption that people could do year after year? Does it really knock the economy down to do this? And by our analysis, the answer to that is no. This is the consumption loss. Once again, it varies depending on whether you bank or not, and some of these funny variables have to do with the fact that you have to take account of what's going on outside the United States. So we have other countries doing things which tends to have trade effects which influence these numbers. But the main thing to see is that you get a loss by 2050 that you would be about 2% poorer than you would otherwise have been. Now, this is a model. So what should you think about a model like this, first of all? This is a model. The model is not able to make all the mistakes that we make when we design legislation. So it operates, it doesn't know about all the ways that we can do this poorly. So you don't have to believe the numbers 2. Multiply by 2. Maybe it's not 2, maybe it's 5. Maybe it's 5% less. I mean, you don't have to believe this model is accurate. I don't believe it's that accurate. But the point to see is that in this calculation, the United States income and consumption is doubling over this period. So maybe if it's a 5% loss by going up by 100%, only goes up by 90%. The point I would make is that there's a lot of money involved here. It's billions of dollars, but in an economy the size of ours, the cost is the loss in terms of consumption, in terms of your standard of living, is in the noise of the growth forecast. It's within the noise of our uncertainty about what growth will be over this period. That's not what the problem is. What about employment? Well, in the longer term, employment is a matter of monetary and fiscal policy. Even in the short term, employment is a matter of monetary and fiscal policy, as is obvious as we watch our Federal Reserve struggling to do this. That's not where the problem is. The problem is that there are winners and losers. The problem with this issue is that there are particular sectors, areas of the country, employment groups and stuff, and relatively poor people for whom this is a serious business. And then there are the issues of the scale of the change that has to take place and whether or not we are prepared socially to put up with that level of change. It's not so that another thing I'd like to carry away is that when you hear these arguments that the climate problem, doing the climate problem is the destruction of the economy and all that, that's just wrong. Mm-hmm. There are people who argue that, but it's just wrong. It's not correct. There are serious problems of distributional and for particular groups, but for the country as a whole, but we could do this with but managing it is a real problem. And one way to see that is to look at the scale issue and what has to take place. So one way to look at that is to look at how the energy system adjusts. Now, I will tell you there's some funny behavior in here because of our assumptions about other countries joining in, and when other developing countries come in, it has a big effect on trade. But the basic point will be easy to make. So here is what this is. This is 2005. Oops, no, I don't want to do that. This is 2005, and that's 2050. So this is a measure. This is, techie folks use numbers like this, exajoules. I don't know exactly what an exajoule is, but it's a measure of how much energy we use, total amount of energy that goes into our system. And so in 2005, we're using about 100 exajoules in the United States. And you could think, I don't know how to convert this into barrels of oil or tons of coal, but you could think about equivalent.
An exajoule is about the same as
all right, for those of you, that's helpful.
I'm not sure that helps.
An exajoule is about a quad. It's off a little bit. It doesn't really matter what the units are, because I want to give you the feel, the scale of the problem. So this is the amount of coal we use, and that's oil. That's natural gas, nuclear, and the blue is non-biomass renewables. So the current renewables don't really show in 2005, it's too small. So if we did, this is a scenario, if we had no climate policy in the United States, we would walk up the tops of these bars. And so we would go from 100, we would go up, income roughly doubles over this period, but we would go up by about 60% in total energy use in the economy. We don't use, the energy doesn't go up directly with GDP, because we get more efficient all the time. So let's just look out to 2050. What would happen? What would have to, by this scenario, what would have to be done by 2050? Now, this is one scenario. There are many ways to get to 2050 and reach this. This is just one case, but it will make the scale point that I want to put across. And that is, we have to get the carbon out of the power system. We have to get the carbon out of the electric power system. And a little bit more than half of all our electric power in the United States is generated from coal, which has got a lot of CO2s per unit of electricity. Let's go back. So first of all, you have to get it out of demand. So you have to get, call this conservation, call it efficiency, call it demand reduction. You're going to have to get the demand down. This will take place by having higher prices and other technological changes and such that would lower the total demand. So you have to get part of it out of demand. After you've gotten that amount out of demand, there are two big problems. There are two big issues. You need to get the carbon out of the. God, I see an old friend sitting there. Look at that. How you? I see a familiar face. You have to get the carbon out of the power system, which is to get the coal out of the power system, or at least you have to burn the coal in the power system and not create the CO2. And you need to get the carbon out of the cars. So how do we get the carbon out of the power system? Cars. Well, you need more efficient cars, and we're moving to that with CAFE standards and other things. So that's implied in here. But even if we get more efficient cars, which we're processing to do, the way, if you're going to achieve this target, you have to somehow get those emissions out of the cars. In this particular scenario, biomass is used, and biomass is the major method that we are pursuing in the United States to do this, particularly under the current administration. Now, this is just a scenario, but to give you the feeling of the scale, that amount of biomass in the United States, if we did that, that would require the total existing cropland of the United States to grow it, to give you a feel of the scale of the energy system. Now, what about CO2 cap? We could do CO2 capture. But here all the CO2 is being emitted. Over here, almost all the CO2 is being captured and stored in underground. The way you do that is you build a different kind of power plant, and you generate the electricity. You It's expensive, but you capture the CO2, you can pipe it somewhere, and you can store the CO2 in underground geological reservoirs. And every step in that process is one that we've done in some fashion somewhere. It's not a big scientific puzzle, but we have not done it at scale. We've not done all the integrated system. And the scale problem comes because this implies maybe 300 to 400 of these plants by 2050. 300 to 400 plants at the level of 1,000 gigawatts, 500,000 megawatt plants. Really, really big plants. And I'll come back. I'll come back to that. So that and one of the real difficulties, and the current legislation tries to deal with this, is not that the economy couldn't deal with this, but if you're in the coal business, to go down this path is really going to be hard. And so one of the big problems in designing a policy that would achieve any of this is you have to somehow deal with these distributional effects. Now, there's another thing happening that's not well understood, but we're going to have to deal with this. And that is what's happening to the cost. A lot of these technologies, particularly the carbon capture and storage, let me back up one step. I didn't say anything about nuclear. In this case, we held nuclear constant on the assumption that nuclear would be difficult to expand politically. I'm going to show you I'll show you another case where nuclear is allowed to expand. Also, we don't have as much I think we don't have as much wind and solar as probably should be in this kind of projection. But multiply it by 2 or multiply it by 3, you still have the same kind of challenge that I'm talking about. So.
What about 2035? It looks like an odd year.
Yeah, this is what happens. This is one of the things that, what happens here is that, and once again, the model probably moves faster than the world would do. But what happens is that this is what I said about the fact that if you're going to make an analysis of what the United States is doing, you have to make some assumption about what the rest of the world is doing, because there are trade effects. And one of the things that happens is in 2030, 2035, we have the developing countries coming in and taking substantial commitments. And what happens here is early in the process, we're actually making a lot of biofuels in the United States, but we're importing most of the biofuels in the developing world. And when they begin to take commitments, they absorb the biofuels. And so the biofuels, the lesson here is the biofuels industry is going to be sloshed around and through trade effects, just like because biofuels trade off with oil. So that's what's going on there. These are the kind of this is the scale of the challenge. And one of the problems that we have is a lot of these technologies are relatively capital intensive, and something is happening to the cost of large capital construction. This is an index of capital cost index. It's for the power sector, electric power sector, and this is an index from 2000. And let's look at 2004, and let's just look at without nuclear power. Look at the cost of electric power construction, and this would also apply to carbon capture and storage. If you put in nuclear power, it's even worse. The cost of large-scale capital construction, which is part of what's going to be needed to deal with this problem, is going up so strongly right now, driven by China and India, largely. The demand from China and India and other developing countries, which are putting pressure on limited resources, steel, fabrication, consulting firms, design engineers, startup engineers, the kind of people that your engineering school is supposed to be producing. Get more of them out there, because the people that you need to do this are being stretched by the pressures, and so pressures of growth not only in the developing countries like China and India, but also in the U.S. and other countries. So now it could be that nuclear could be. This is another point. The other point is that we need to be developing these capture and storage projects. We need to be doing serious investment in R&D and demonstration of these big plants. The problem is, one of the problems is that we're moving in the wrong direction. In recent years, there were a number of proposed plants. BP had a plant in Scotland. They canceled it because the government delayed the subsidy award. Shell had a plant to charge into a reservoir, offshore reservoir. Costs went up. They canceled it. Sask Power was a Canadian project. The trouble is that the cost went from 1.7 to 3.8 billion. They canceled the project. The major U.S. investment in developing this technology to capture and store CO2 was called FutureGen. It was a cooperative project between the U.S. and a whole group of industries, coal and electric powers, and that has been, I don't know if you call it restructured, canceled. It's been stopped, largely because of what happened to the price tag. The tag went up and the government was holding the bag, and the Secretary of Energy canceled the project. So I'm coming to a point about, are we taking it seriously? We're not taking it enough seriously to kind of keep pushing through to get this work done, even with these cost problems. If we went to nuclear, once again, in the first case, I held nuclear sort of constant. If we unleashed, if nuclear is limited, if we unleashed nuclear, then nuclear would grow. If we let nuclear grow as an economic matter and we put on these carbon charges, nuclear would become more cost effective in the United States. So nuclear is a possibility, and these are two extreme cases. So the truth is probably somewhere in the middle. But my own view is we cannot do all this capture and storage, and we cannot do this without some nuclear. We need some of this. And so that's back as to whether we take this issue seriously enough to do that. The other point I'll make about the importance of capture and storage is this. This is a picture of electricity generation. Once again, I'm always imposing this 50% reduction without capture and storage. If you had no capture and storage, now you can do it. I have two cases here. There's a case with nuclear limited, nuclear unleashed. Actually, with nuclear unleashed, the coal actually kind of lasts longer. Coal stays in longer. That's because if you had more nuclear and you weren't squeezing the economy so hard to get the carbon out, the growth would be higher. That's why that's happening. But the point is, if you're going to meet this target and you don't have capture and storage, this is what happens to the coal industry. Now, that can't happen to the coal industry politically. So it indicates the importance of this technology. Biomass. I just make one point. We're working hard on biomass. There's a huge amount of work going on biomass, but there's a limit to what we can do with biomass. And this is not corn. Corn ethanol is a terrible policy. This is cellulosic ethanol, which is not quite developed, but I think we will develop it, and a lot of work's being done. But if we were going to achieve this 550 target, and you're going to use ethanol, or you're going to use biomass to meet that kind of target globally, if we're going to do this globally, what would it take to grow that ethanol? Now, this is another model result. I don't claim that this is the best work. It's experimental work, and this is an early example of the work. But it does give you the idea of what the scale of the energy system is if we want to make this change. So look at, oops, is it going to work? Sorry. I'm going to show you a picture of the world, and I'm going to show you the picture of what portion of the world, by a fraction of the land surface, by this particular calculation, is growing biomass. So there you are. This is 2010, and just watch. It'll go 2030, 2040, 2050, 2060, 2070, 2080, 2090, 2100. So it indicates that if we're going to solve this problem with biomass, it's going to be a big problem. This is not necessarily the death of the food system, because it's not necessarily grown on food lands. But if you look at the effect of unmanaged forestry, natural forest lands, this is natural forests. So you would have biomass encroaching on natural forests. So you see gradually over time that biomass is encroaching on natural forests. Now, this is already happening now, of course, but this is just an indication of the nature of this problem. So now we can get out of this problem to some degree, the biomass problem, because in this calculation we used the biomass to get the carbon out of the cars. Well, there's another way to do that. You can do that with a plug-in hybrid. You can get electricity into the cars, but then you're back dealing with the electricity problem. In my own view, is that the plug-in hybrid and moving the automobile energy some into electric power system is a part of the story, part of the answer. Biomass is a part of the story, but I think another message to carry away is we're going to have to manage this carefully because there are important interactions between these things. One good side of this is if we auctioned all these permits, then there's a lot of money. This is two cases. There's the 50% reduction case I just showed you, or there's the stabilized in 2005 case. And this is the amount of money you would collect if you auctioned these permits, which is what a lot of the states are doing in the New England system, in the RGGI system. So you're talking about hundreds of billions of dollars. This is a large source of revenue, which is going to be spent in various things, including R&D and subsidy and such. So so that although this is a lot of money, it's a lot of money out of consumers' pockets. It also is resources that, if used well, could have a big effect on this story. Now, that's giving you a picture. I've given you a view of what I think is necessary. What do you think of the technologies we ought to be using? Technologies to do with this that we would definitely use, probably use, not sure, probably not use, definitely not use. Some of my colleagues have done a lot of work in surveys of people about this. What does the public think is the answer to this question? So I've given you my view. Now, what does the public think is the answer to this question, to those questions? You can think of what you think the answer is. So they give them a choice of solar energy, energy-efficient cars, that's good, wind energy, carbon sequestration. This is carbon sequestration by planting trees and tillage practices. There's bioenergy, biomass, that's what I was talking about, growing fuel, nuclear energy, and carbon capture and storage. And this is the US. And what you see is if you ask people if you ask in a survey, what do people think? People think energy efficient cars, that's true, that's really important. But there's a perception that the answer to this problem is in wind and solar. Now, wind and solar is important. We need everything we can get, but wind and solar is small. It's small certainly on the 50-year horizon, even small on the 100-year horizon, even with the most rapid growth that we can hope for. And if you look at things that I've said I think are important, like nuclear energy and carbon capture and storage, it is heavily rated as something probably we shouldn't use or definitely not use. This is, I think, more a reflection of people's understanding, not judgments based on good understanding, but people don't understand what these things mean. And this is the US. It's interesting that if you do the same thing in Sweden, you get very similar answers. And if you do the same thing in the UK, you get very different answers. This is not a US perception. This is a perception of at least the US and Western Europe, very similar. The other thing about dealing with this as a political issue is, what are people willing to pay to solve this problem? That is, it's a problem. So, and it's going to be costly in terms of consumer budgets. So what are people going to be willing to pay? What do people think is a reasonable increase in your budget to solve this problem? Now, this question was asked of people where they were given some idea of what the damages are from climate change, which was scary, like Steve Snyder and such. And they gave them the word solve. Now, you know from sitting in the last 40 minutes that the word solve isn't the right word. Solve is a stronger word than manage the risk. But they gave them solve. So you got a number in your head? What do you think it's worth? What would you pay? I mean, in terms of your monthly bills, what do you think it's worth? What would you think you'd be willing to pay? What do you think your neighbors are willing to pay? And the story looks like this. This is the result of a survey. Now, once again, the survey is not perfect, but it indicates a problem. this is the monthly willingness to pay, meaning increasing your consumer budget, gasoline, electric power, increased cost of food, and I don't know, trips to Malaga or whatever people in Dartmouth do when they leave town. Well, there are about 50% of the people that wouldn't pay more than about $10 a month. There are about 5% of the people that pay as much as $100 a month. Now, the numbers I gave you before imply numbers more like $100 a month than $10 a month of what would be out of the consumer's pocket. Now, what does this mean? I'll give you my view of what it means. I don't think this is necessarily an indication of people not caring about the climate issue. It's what people think it's going to be. It's not generally understood the scale of what's going to be required to deal with the problem. And that's a function of this being an extremely complicated problem, and not many people will come and sit in an auditorium like this for an hour and listen to somebody like me. Most people won't do that. So they don't know. And the other thing is our politicians aren't helping. Now, a very interesting thing is going to happen in the next few weeks. Al Gore, how many people have seen An Inconvenient Truth? Okay. Al Gore is raising $300 million for a project he calls We, or something like that. And he's going to spend $300 million on television advertising to try to get action, to try to go beyond An Inconvenient Truth and bring people to demand action. And I think one thing that's going to be really interesting is how much is he going to explain about the problem? And I think this is a very tricky challenge, because in preparing a talk like this and talking to you, I realize I kind of ride it along a knife edge between I either can inspire you that this requires more effort and you work harder and go out and do it, or you go a little too far and you think, oh, to hell with it, just go and flop into despair and say, oh, well. So it's going to be interesting to watch what they think is the right thing to do, because I don't think people understand what the scale of the problem is. We could deal with it, but we don't seem to be willing to say, this is a challenge, it's going to require sacrifice, et cetera. It's all sort of buy a light bulb and you'll be happier, and that's not quite right. So where are we?
I have a question about that nice picture.
Yeah.
Does that assume that the population thinks that the government is competent and honest and will run the thing right? Very crucial.
Yeah, when you do this, I think this is a question which is largely abstracted from that. So I don't think this is a question that, the way it was done, probably doesn't elicit the notion I wouldn't pay anything because I think they throw the money away. The other thing I would point out to you, which I forgot to mention, is that on this figure we have Japan, the US, UK, and Sweden. It's interesting. Maybe this is not, maybe there's not quite accurate, but it's interesting. There's not a big difference between the countries, and I think I think the way this question was asked probably does not elicit that. There certainly are reasons to be concerned about that. About if we go after this, are we going to screw things up? So where are we? Personal view. Cap and trade system is a good way to go. Lots of people favor other approaches like taxes and more regulations, but the reduction targets in this current bill are too ambitious. Whether that's a big problem now, whether we'll adjust later, we could talk about that. There's a poor consumer understanding, I think, of what it takes to deal with this issue. And the distributional issues are going to dominate. And because we have a hard time dealing with the distributional issues, we're going to put in a lot of regulatory things that are probably going to make it more expensive. The U.S. could afford to lead. That's the message I would give. We could afford to do this. It's not a growth killer. And we could adjust with learn with response abroad. That is, if we can see what other people do, we can take measures step by step and move. And it's not that we don't today commit ourselves to continue to shoot ourselves in the foot, and the Chinese don't do anything, and we'll shoot ourselves in the foot every 10 years for the next century. I mean, you can adjust depending on what they do. The question is whether we start. But we're not yet taking the issue seriously. We're slow in putting a price on CO2. I think with the most optimistic that I can be is that we might get this on the agenda in 2009, provided that it can compete with welfare reform and the deficit and the recession and the immigration and Iraq. I mean, it has to get up to get presidential attention, but I think a good chance that it will. But it wouldn't pass until maybe 2010, most optimistic. Maybe go into effect in 2013. So it takes a long time. There's a long lag here. And I think we're not spending as much as we should on R&D, on capturing other technologies. This is a large issue, which I now have to stop talking, so I won't say much about it. But I think it's not just the amount we spend, but it's not clear we have the right institutions in the government to spend the money, which comes maybe come back to your point. And so I think even 550 parts, these targets are going to be very hard, to meet. So if you come out with this view, and you're like me and you work on this every day, how do you get up in the morning? And this is the answer. There's a hope. Remember, you need to take a risk management focus to this. This is a century scale problem. This is not a problem we solve today. It's a century scale problem, and the risk builds with time. Second, not to lose heart over the difficulty of particular targets. I think it's dangerous to focus on 550. If we don't do this in the next 10 years, it's hopeless. Or if we don't meet 450, it's hopeless. You hear this kind of talk, particularly from environmental advocates, as they use that as a tactic to inspire people. But what happens if you can't? And even modest mitigation measures reduce the worst outcomes. Here's the point again. Let's just look at this as a risk management problem. Let's pick two areas, more than 3.8 degrees global warming, or more than 2 feet of sea level rise by our most recent analysis. And these are preliminary. As I said, we have our probabilities are somewhat worse than this right now, but this makes my point. There's a 1 in 10 chance of greater than 4 degrees C. 4 degrees C is deadly serious business, particularly in the Arctic, and what that all means. And greater than 1 in 6 of more than 2 degrees sea level rise. If we could stabilize at 550, which I say is difficult, not impossible, then this is an uncertainty analysis, so we only had 250 runs, so it indicates that the probability is really low. Because if you can stabilize at 450, then you have ruled out the possibility of this really nasty outcome. That may be hard to do. It wouldn't be hard to stabilize at 750. And almost anything we can do helps lower the probability of these nasty outcomes. Even if you could only stabilize at 750, I told you that doing nothing only leads us to about 850. If you just hold it down to 750, it lowers the probability of this from 1 in 10 to 1 in 29. So what's going on here? Now, pardon to the people who are not used to looking at probability distributions, but for that portion of the audience that is used to this, I'll go through this. These are like bell curves. They're like probability distributions of the global temperature change. And you'll notice it's got a what the probability people call a fat tail. It's got a big tail on the right. It's the nature of this process because of the feedbacks in the system. And so if you had no policy, you have this. This is just another picture of another way of reflecting what was in that wheel I showed you, first wheel. And if we had the 550 policy, you shift this to this, which is what I had in my other wheel. And the point that leads you not to lose faith, even if it's going to be hard to do this, is the following. The median, that is the 50% more or 50% less, is around 2.4 in this case with no policy. And if you could stabilize at 550, you don't have a big effect at. You lower it from about 2.4 down to maybe 1.7. It's not something you run down and run home and tell your grandmother, we solved the problem. But the important thing that happens here is what happens to the tails. These really bad outcomes in the tails are drastically reduced. You reduce the likelihood of the worst outcomes. So almost anything we can do has its biggest effect on the really nasty outcomes, the things that are out in the tail, out in the fat tail. So it is a reason not to lose heart. So Why take it seriously? Well, this is my final walk through the litany. It's not proven. This is a common argument. It's not proven. This is the wrong question. Wrong question. This is not a true-false question. It's not a question about is climate doing something? Are we affecting climate? Or are we not? It's a question of what is the risk of what we're doing, and what is the appropriate response given the risk we're creating by what we're doing. Not that serious. Well, it's not. It's serious by our analysis. The risk is very serious by our analysis, and even small levels of climate change are risk to some ecosystems and some people in some circumstances. So it's it's your own judgment of how serious you think it is. But if you take our risk estimates, it's hard to argue that it's not. It's hard to argue that we ought to be devoting more effort than we are to managing this risk. It's too expensive. Well, not with intelligent, well-timed measures. The problem is not that it's too expensive to the economy. The problem is that it's so hard to deal with the distributional effects. It's so hard to think of ways to compensate the people who are hurt along the way. We were talking earlier about trade legislation. Same problem. Most people are not against trade. They're against hurting people. And the people who get hurt by trade are very specific people. And the people who benefit from trade is all the rest of us. And it is the same kind of problem. Even if we do, the Chinese won't. Well, we need leadership. We need leadership. And we can adjust to their response. You don't have to march on for decade after decade if we can't find a way to assist, to get them to assist. My own view of this is that we need leadership. The leadership really missing now is out of the executive, because it's very hard for the Congress to do this. I think that it may take time. This is a century-scale problem. The Chinese economy is seriously threatened by climate change. They already have serious problems, particularly with dust, and they have water problems and the like. So it's not as if China was sort of oblivious to this. It's not high on their priority list, but this could happen. It could come there, and another reason to do much more on the R&D side is that the way we get China to take this more seriously is to find ways to lower the cost to them of doing this, which is a technology research question. And it's too late anyway. Well, it is too late for some arbitrary targets. This is my view. That is the cost of not hitting those, not making the cost of stopping at 450. I just don't think it's socially going to be possible to do it. But it's not too late for efforts to reduce the most serious environmental risks, and we ought to be about the task. Thank you. So you want to?
That's it?
You're going to moderate?
I will if you want me to.
Sure, do. Because
All right, well, we have time for questions. Over here, please.
Thank you. In the 3 years that I've been actively exploring this whole issue and flagging pretty much every outlandish, fix that seems to be floated, in just the past 2 months, I've seen 2 articles. One was in our local paper, and I lost track of it, so I lost track of the name. The more recent one was in the New York Times probably a month ago. And both of them focused on different catalytic materials that act as carbon sinks, permanent carbon sinks, and both very active catalytic agents. One of them that I lost track of, I translated into the word zeolytic something or other. I Googled that, so I obviously didn't come up with anything, but that's the closest I came. The second one from the Times I could track down. Both of them did not come with any flags attached. They're both inexpensive materials to produce. They're both highly active absorbers, and both, nothing toxic about it, et cetera, et cetera, et cetera. Nothing on the face of it that presented any major problems. Enormously cost-effective and carbon absorbers to, on the scale of 1,000 to 1 by weight. I mean, just the kind of thing you'd love to see. And so I'm wondering if you'd have heard.
Well, I'm sorry, I didn't see that article.
There's two of them.
There are people looking for other ways to deal with this? I mean, first of all, you got to capture the CO2. So that's
Well,
the first.
capture it and then permanently store it.
Yeah, but you got to. There are two. There are a couple of.
That's why I'm saying they are catalytic absorbers.
Right, but
Yeah.
the question is, do you start with the CO2 at the concentrations it is in the air, or do you start with pure CO2? So if you're gonna, most of these, a lot of the technologies for storing CO2 have to do with, first of all, you have to separate pure CO2, which is the first problem. That's where the big cost is. Yes, so separate the CO2 itself. I'll come back later, if you want, to some ideas around about taking CO2 out of the air, but that's another question. So I really don't know about that. The key technology people think is going to be cost effective is to charge the CO2 into deep saline aquifers, where, or into abandoned gas reservoirs or what have you, where it would stay for long enough, thousands of years. There are ideas that there are materials that take up CO2. And so I'd have to see this. I have no doubt there are materials that do that. It'll come down to the question of what is the scale? You know, how many million tons of the material do you need to take up the CO2?
Right, these were remarkable
But I haven't
materials.
seen that.
Yeah.
I don't know.
Okay.
Yeah.
Yep.
Over here then, please.
Maybe one of the engineers here knows.
Or is it, wait, who's Tom? Yeah.
Sure. Yeah, I had two
The
questions.
microphone is coming at you, so.
Thanks. I had two questions, if you don't mind. My first was, I noticed that you said towards the end that you thought the Lieberman-Warner targets were too ambitious. I was wondering if you could elaborate on that a little bit for me.
Well, if we really thought we were going to meet those targets all the way out to 2050, I think that they imply levels of pressure on the society, that is, the amount you'd have to do in terms of carbon capture and storage and the like, that I don't think we're on the path to doing. So if you can't get hundreds of those plants built, if you're not willing to build hundreds of nuclear power plants, then to get the carbon out of the system, you're going to have to raise the prices higher and higher and put more pressure on to get it out of the demand side. So I think that we just aren't on a path to get those technologies put in place. So now they have targets along the way. They have a 2020 target, which is return to 1990. That might be possible. But it's just my reading of all that has to be done over such a relatively short period of time. And if you want to do windmills, you know, you're talking about millions of windmills or solar collectors and such. So it's my sense of how hard it's going to be to get these large capital investments done, and what it would take if you can't get enough of them done to squeeze it out of the demand side. It's a personal judgment.
My other question was, you spoke a lot about, you mentioned several times R&D money. You'd like to see the government pouring more R&D into basic research for carbon capture and alternative energies. And, I've heard some of the rhetoric out of the McCain campaign. They're saying that what they'd like to do is they'd like to just set a price on carbon through a cap and trade system and get rid of all of the technology-specific regulations. Like, they don't want to deal with CAFE efficiency standards or renewable portfolio standards. And I'm just curious how you think that would play out if we just put a price on carbon and let the economy run with it.
Well, there are three things here. There's the price that you come to the cap and trade system. There's the regulations, CAFE, renewable portfolio standards and stuff, and then there's R&D, which is a separate thing. So, what we're doing with CAFE, we've decided to do it. I wouldn't undo it. I don't think that CAFE is a very efficient way to go about this. CAFE is not. I would prefer to see this done with the price than with CAFE. Now, what CAFE is, for those who are not what CAFE is the corporate average fuel economy standard. So, a manufacturer like Ford, for its fleet of cars in the United States, let's talk about the SUVs for a minute, have to meet a standard as an average of 21.7 miles per gallon. Have I got that right? 21.7. And that now, there's new legislation, they have to increase that to 35 miles a gallon by 2020. Right? Have I got this right? All right. And there's a somewhat different for SUVs, and it's more complicated than you'd explain in a short minute now because the legislation's changed. But essentially, it tells the manufacturers you cannot sell your fleet of cars as a whole can't have a fuel efficiency worse than this amount. So what it does, if they want to sell their more efficient cars, their more profitable cars, which is your Ford Explorer, they have to subsidize the small cars. If they lose small cars, they shift and they try to get technology and stuff. They're doing that. Now, so I'm not for abandoning the standards we've got. Let's leave them. That's fine. Let's put them in effect. But that is not my preferred way of going about this for a couple of reasons. The standard. If you increase the efficiency of the car, then it's cheaper to drive, so people drive more. So there's a rebound effect. The other thing is you don't give any incentive not to drive. It'd be much better to have higher gasoline prices because you want to get the response on the. Now renewable portfolio standards. The problem with renewable portfolio standards is that as long as the utility can pass those on, is that they can be terribly inefficient. The utility can go out and sort of, buy your antique furniture and burn it in the renewable. It's not a way to achieve the cheapest way of doing it. So I'm an economist. It doesn't shock you. I'd prefer to see us use the price system to do this. On the other hand, I'm not a theological, I'm not an Ayatollah about this. So I think it's a serious enough problem. I'm willing to say, okay, if we don't want to do some of that, and that's what we have to do. Let's do it. Let's get it done. And so I'm not theologically pure about it.
Let's see other students that would like to ask questions. Back here, yeah.
I was wondering whether the nuclear solution posed a real scientific problem. Is there like a real hazard to this solution, or is it more of a public perception problem of how safe storage of waste would be?
Once again, you're getting the economist version of nuclear engineering. I'll give you my view of it. I think that we can deal technically with the storage problem. Technically, we can deal with it. It's a political problem, and unfortunately, we put the storage in the state that doesn't want it, that has its senator as the chief of the Senate, and so I don't think that is the problem. Given that, it's not that it's if you had a choice of having the nuclear waste go away because you had a magic wand or something, that'd be better than putting it in Yucca Mountain. But given all the other problems that we're facing with CO2 and other things, then I don't think that's a big problem. The problem with nuclear is cost, because it's very expensive, and there are improved technologies on the safety side. So I don't think it's not that it's perfectly safe, but all these technologies have their risks. The real problem on the nuclear side, I think, is the integration problem. And that we have a hard time dealing with the fuel cycle. If we could manage the fuel cycle, if we could control the fuel cycle, then I think it would be better. But one of the problems we have in going further with nuclear is that it's very difficult to control access to the fuel cycle for everybody else. So that's and Ahmadinejad came out yesterday, 6,000 more. Got 6,000 more centrifuges in order to do nuclear power. Nuclear is tied up in a very serious energy security problem. I'm talking about energy security, but one of the part of the energy security problems is the proliferation problem in the nuclear power cycle. So all those are problems to be overcome. I think we're going to build some more nuclear plants in the United States. It's a matter of getting the business model sorted out, and so I think we're going to do that. But we're not going to build them in very big lots of them. Of course, they're building several. There are 12 or so going up in China, Indonesia. A lot of other countries are building them as well.
I'm going to call on Dr. Steckenberger.
Thank you. I'm an cultural anthropologist. When I think about risk, it's usually risk to lifestyles and cultural values, the ways we live and we used to see the environment and so on. And I'm aware that when you talk about risk, you talk about that probably, but about something else. What I would like to ask you is, what exactly do you mean by risk for what? Risk that what kind of thing happens that, you're not talking about change in the environment in general terms, but get specific items or perspectives with regard to society, I assume. What is at risk?
Yes. You ask a good, deep question there. I think of risk, first of all, in the way that I showed, the way I did the wheel. There's a risk of the type of temperature change that we could see. So, but the temperature change is only a kind of a symbol of climate change, because climate change is really precipitation and soil drying and stuff. So, but the wheel indicates that there are really bad outcomes and not so bad outcomes. So that's that, and so it's and what's the risk of the worst outcomes? I mean, what am I thinking about? I'm thinking about large-scale loss of species, of native species. I'm thinking about perhaps large-scale sea level rise that disrupts some societies severely. One thing that I worry a lot about is the flow of water off of mountain glaciers. A number of areas in the world, particularly in Peru and in the Ganges Plain, some degree in Colorado and the western United States, you have rainfall and snowfall. Snowfall's in the mountains, and the snowpack in the mountains is the storage device. It is the reservoir. And so during the non-rainy season or non-monsoon, you have water that people are using to irrigate with. And one of the risks is that because of temperature change, you completely change that flow pattern. And so what happens in the Ganges Plain, where there are hundreds of millions of people, if the pattern of flow off the Himalayan ice cap, which comes down the Ganges and the Brahmaputra and all that, changes? That's what I mean. So it is, it's a kind of maybe the economist version of the world, but it affects whether people are going to survive there. That's what I mean.
When you talk about risk, that's the second level of
Mm-hmm.
talking about.
Now there are other risks. We could go on. I mean, there is disease risk. There are disease vectors, spread of cholera, dengue fever, malaria. All those things. So there are lots of things that influence humans, but also a lot of things that affect natural ecosystems that we don't understand, and we don't necessarily fully understand our level of dependence on those systems. There are also some super fat tail risks that are worse, which is there are possibilities that the ocean circulation could change, which would make a big difference. There are possibilities of outgassing of methane and carbon dioxide from the Arctic.
Are you assessing the costs of those risks if you don't do anything in comparison to what it costs to do something about it? Well, I'm sure there are.
This is an important question, because economists love to do benefit cost analysis. You want to cost those things. I'll just tell you that people do that kind of work. We don't. I'm of the view that a lot of things we could cost, a lot of things we know how to do, that economists know how to do. But now we're talking about things that are outside our sandbox. And I don't mean there aren't economists that do that. What's it worth to have the tundra? I mean, who in the hell knows what that means? So I think in a lot of those areas we don't really have a way to put social environmental effects into a common metric. We're off in a very deep conversation here about it.
Maybe one more question,
Yeah.
I think. Who is most urgently needing to ask
We have an
a
urgent one
question?
right there.
Mine's a short question.
Yeah.
I just wondered if you could say a few words about the relation between the rate of emissions and the accumulation of parts per million. It seems to me as if it's probably highly nonlinear and will affect everything you've said. That is, once the stuff is emitted, how
Yes.
long does it take to go away, and how does it change the absorptive properties of the earth, and so on? What is actually known about the relation between emission rates and accumulation of parts per million?
I think a lot. We're talking now about the carbon cycle. We're talking about carbon dioxide. So carbon dioxide has a kind of an average lifetime in the atmosphere of the order of 100 to 120 years. So if you drive home, some of that carbon dioxide will be there 1,000 years from now. But most of it, but on the average, it would be up for maybe 100 to 120 years. Now, that lifetime in the atmosphere is when you emit carbon dioxide, about half of it right now stays in the atmosphere. About half of it is absorbed over the next decade or so, absorbed in the ocean, and about half is absorbed by terrestrial, soils and bugs in the soil and trees and stuff. So that relationship is pretty well pretty well understood, and people can go back and look at what they think the best estimates are of CO2 emissions in the 20th century, and then approximate that and look at what the measurements are in the atmosphere and see. So they understand that pretty well. As you go forward, the system changes. So if the carbon dioxide gets very high, the ability of the ocean to absorb it goes down. So the lifetime extends. And then there's a question about the CO2 is absorbed in trees and stuff because CO2 is a fertilizer. There's a carbon fertilization effect. A lot of plants grow faster with CO2. You know, you go to greenhouse gases, they artificially put CO2 inside. But there's a limit to that, which is not fairly well understood for large ecosystems. So I think we know that fairly well, and I think one of the difficulties of this issue in explaining it to lay people is that it's very hard to get people to get a person who's not thought about this very much to understand that when you put it up there, it stays a long time, and you can't get it back down. This notion of the stock you're creating. Is that responsive to your question?
There must be some assumptions made about what will happen if the emission rate is reduced in terms of how that will influence the parts per million. Yes. That's what people like us do, and people build. But I would say that there's a good deal of uncertainty about that. Uncertainty about the ocean circulations, uncertainty about plants and stuff. And so, but I think the process is pretty well understood. And one of the things that's difficult, I'd say, for people who haven't actually done these calculations to see is that if you wanted to stabilize in the atmosphere CO2 like right now, you'd have to lower CO2 by 60 or 80%. You have to stop putting it up because it's a stock. But there's an industry out there called carbon cycle modeling where people do that. And so there's uncertainties, but it's not that it's not understood pretty well. It's not understood better than a lot of the other parts of the system.
I think we need to close the formal part of this and say thank you.
Okay. Good.